Good afternoon, this is Schweitzer, and we're going to run a quick little video here on limiting reactants and just general stoichiometry calculations. This is something that is really critical to everything we do in stoichiometry, and you got to be good at this. Are we doing enough problems here to become an expert? The answer is no. So you need to make sure you're checking yourself to make sure you can do these types of problems with your eyes closed. This is a quick little preview of this, or post view, something that you should have seen already. If you haven't, then you're going to need more work at it. So we're just really introducing these concepts. Alright, so first of all, what is a limiting reactant? It's when things are running, whenever you're building something, it doesn't matter if it's chemistry or if whatever it is. Whenever you're building something, you're consuming reactants. This is something that we would, consuming raw materials, and we would talk about this in all sorts of terms. But we're consuming, starting material. So how quickly are you consuming starting material? How much starting material do you have? Those are the two main concerns here. So what is your rate used? And how much quantity do you have? So neither of them are any more important than the other ones. But you want to be able to use and think about them. This is a situation where we want to be able to do it in our heads without any math, if we can. If I can determine the limiting reactant without doing any math, that's what I want to do. So in this thing, I'm going to also introduce the idea of an ice table and show you some basic calculations. Alright, so here we go. X and Y are combined to form XY. Alright. Rate used, quantity. The numbers out front here, 1, 1, 1. These numbers here are your rate used. Okay? So these are being consumed at the same rate. Therefore, quantity plays the pivotal role. I have less of the Y. It's being used at the same rate. So this is my limiting reactant. What I'm saying here is that if I consume all of my Y, which I'm going to, how much of XY will I get? If I consume all of my Y, how much X will be left? It should be a positive value. So let's run out a typical ice table. Initial, stoich ratio, end. Okay. Now again, this is just basic stuff here, but really we would do a lot of this, and we're going to do a lot of it as we move along. So 10, 5, 0. I run my limiting down to 0, minus 5, down to 0. That indicates limiting reactant. Alright? From Y to X is a 1-to-1 ratio. So 5 Y's, get rid of Y and go to X at a 1-to-1 ratio is 5x. So whenever I solve for a reactant right here, anytime I solve for a reactant, we consider it a need. If I consume all my Y, which I'm going to, how much X do I need to go with that? And the answer is 5. 10 minus 5 is 5. Now again, one of the bugaboos here is kids think they know everything, and they're going to just say, I can do that. That's no problem. No. This is basic stuff, yes. I know you can do a lot of this math in your head, but eventually you won't be able to. And you have to be able to follow these sort of methodologies. 1-to-1 ratio, 5y, get rid of 1, get rid of the y, go to the xy, and it's going to be 5 plus 5. And 0 plus 5 is 5. So I'm showing all the steps. Keep in mind, no work on an AP test means you cheated off your neighbor, and therefore no answers. No, nothing. And this is the work right here. No credit here if you're not showing work. This isn't usually considered work. Okay, just so you know, on an AP test, you can show a stoich ratio, but that's about it. Okay, here's another scenario. Equal quantities, but this has got twice as fast used up. Remember, neither of these are more important than the other one. So Therefore, this is my limiting reactant. Now, if I mistakenly choose the wrong limiting, what happens? Let's try it once. We know this is limiting, but what happens if I use this guy? Alright, so initial stoich ratio n, end, 10 and 10. Okay, if I run this one to 0, minus 10 to 0, that's fine. That's a different math problem. It's not the one we're looking at here, it's a different one. It says, if I consume all my y's, how much xy will I get? And at a 1-to-1 ratio, it would be 10. But let's see what happens here. If I consume all of my y's, how many x's do I need? Alright, well I got 10 y's. For every 1 y, that number right here, I need 2 x's right here. Equals 20x. What do you notice here? Minus. Why am I have the minus here? Because it's a reactant. I'm losing that when I start my building process. 10 minus 20 equals negative 10. If you get a negative value here, okay, that just means you chose the wrong limiting. It's not a lost cause. It just means you need to start over and use the other limiting reactant. Okay, well, let's go ahead and let's do that quickly. I'll erase that. And let's grab this guy. Initial stoich ratio end. Okay, I got 10 of these, 10 of these. Now let's run with this guy. Minus 10 goes to 0. That's not my limiting reactant. 2-to-1 ratio. 10 x's at a 2-to-1 ratio equals 5 y's. Minus 5. And I know it's tempting to not show your work, but it's all about habits. 2-to-1 is also a 2-to-1 ratio, which equals xy would be plus 5 xy's. And that's my answer. Okay. Now what about this guy? In this one, it looks a little bit different because, well, my rate used is indicating that this might be my limiting reactant. But, okay, also I have less of it. I have 6. That indicates limiting reactant. Both factors are indicating limiting reactant. Okay, so without a shadow of doubt, this is my limiting reactant. Minus, so initial stoich ratio end, 610 minus 6 to 0. Let's jump from here to here. Okay, so it's 6. Get rid of x's, 2 x's for every 1 y. 6 divided by 2 is 3. Minus 3. And this would be plus 3. It's the same math. 10 minus 3 is 7, and this is how much I have left because I had done to begin with. Alright? Both factors there are pushing in that direction. Okay? Now, I'm going to try one more thing here. Let's say we turn this around. Okay, we'll add this in here. And let's say I have 2x plus y yields z. Alright? But what happens if I have 6 of these and 10 of these? Okay. Now, this is a scenario where we might, you could probably do this in your head. I'm not saying you can't. Okay. But eventually, our proportions and our ratios won't just be 2-to-1, and it's going to be, you aren't going to be able to do it in your head. So, first thing we do, step 1, is can we get the limiting reactant in our head? You know, just thinking about it. If we can, without a shadow of a doubt, using not guessing, using proportions, you know, and rates used, can we get this? Okay, well, this is looking like the limiting reactant here, but this is looking like the limiting reactant here. So they're conflicting. Is it limiting because it's twice as fast, or is it limiting because there's less quantity? And again, I'm not saying you can't get this in your head, okay? But let's try out how would I do this if I can't get it in my head? You know? So what we do is simply this, okay? What do you think? So step 1, just pick one. Okay, and I'm just going to pick one. Let's just pick this 6. And let's run the 6 to 0. So I'm thinking, okay, is that the limiting reactant? Let's try it. All I got to do is solve from here to there. And see, if I consume all my y, which maybe I think I'm going to, how much of my x's do I need to go with it. How many of this do I need? Let's do the math. 6 y's, get rid of y, and go to x. And it's a 1 to 2 ratio, which gives me 12. 10 minus 12 is negative 2. And I would say, unfortunately, I picked the wrong one. I also learned something here. I learned that this is my limiting reactant. All I do is I go 2x plus y yields z. At that point, 10 and 6, okay, this is my limiting reactant. And here's a key thing. Everything is based off limiting. If you know your limiting, that's great. Everything gets determined mathematically from your limiting. Once you know your limiting, just use your stoich ratios to figure things out. Minus 10 goes to 0. 2 to 1 ratio, 10 at a 2 to 1 ratio equals 5 y's. So minus 5 plus 5, same math there. And I have 1 left. There we go. And there's 5 product z's produced. So everything is based off your limiting reactant. Alright, let's jump into some problems that are more typical here. Propane is burned by a following reaction. If after the reaction is cooked, cooled back down, STP, the sample is measured getting 250 milliliters of carbon dioxide, 2 liters of carbon dioxide. How much propane have we burned to produce this product? Okay, so we'll be adding a few things in here. Now notice here on this problem, it's just telling me that I'm getting 250 liters of carbon dioxide. I only have one item here, so this is not a competing limiting reactant problem. I don't have this. All I'm going to do is jump from here to here. We'll be adding in a few little details here as well about how do I go about dealing with liters. Okay, I know that I can go from molecules to moles, and moles to grams. How do I get liters to moles? That's my main back and forth thing. Of course, moles measure, really, these measure the same thing. They measure a number of particles. So anytime I'm doing a stoich ratio, 1 to 5 to 3 to 4, I can do it in molecules. I can do it in moles. They're a linear relationship. Well, this relationship from moles to liters is also linear. At STP, which is STP, and of course you're not a first-time student, so you should note that this is just PIV nerd, PV equals nRT. So if you're not STP, then you can just use PIV nerd to get your moles. But 22.4 liters equals 1 mole. So once I'm in moles, I can jump from here to here. But because it's linear, right, straight relationship, I can use this straight in my math. I'll show that in a moment. Grams really is the only time you can't use the stoich ratio. So my stoich ratio, I can use molecules, particles, and liters. But let's run this. 250 liters, get rid of liters and go to moles. 1 mole is 22.4 liters. This is going to be moles. For every 4 moles of carbon, they want carbon dioxide, this guy. So I jumped on the wrong one. Alright, so it's 3 CO2s to 1 C3H8. Notice there's 3 carbons in here, and there's 3 carbons there. We're tracking carbons here. And grab your calculator. 250 divided by 22.4 divided by 3 is 3.7. Alright? 3.7 moles of C3H8. And of course, at that point, you could convert that to liters, you can convert that to grams, you can convert that to number of particles, as long as you have the appropriate relationship. Now, I mentioned that you can use liters. Really important that you have to go from a liter of something that's a gas to something that's a gas, which propane is. You can't go from liters to solid. It's not going to work. But let's just show that quickly to see how we get the same. Well, 3.7, let's kick this back to liters quickly here. 3.7 liters, get rid of liters and go to, get rid of moles, and go to liters. So 1 mole is 22.4 liters, is 83 liters. So 83 liters. Let's try the math out directly. I have 250 liters. Get rid of liters and go to liters. CO2 to C3H8. This is a 3:1 ratio. 250 divided by 3, 250 divided by 3 is 83.3. Alright? Don't just memorize pathways, understand how they work and why they work. And then you can do whatever you want with them. Note that we have increasing, we go from 83 to 250. And in an enclosed container, that would cause pressure to build up, which is why we use burning reactions to run things. And that's just the carbon dioxide. We still got a lot of water vapor there too. Alright, we got 25 grams of methane is burned and 2 liters of container of 25 grams of oxygen. Answer the line questions. What's the limiting reactant? Alright, so first things first, I'm in grams. So I often refer to this as the cardinal sin of stoichiometry. You cannot use grams in your ICE table. You cannot use grams in your ideas of limiting reactant. I'm looking at quantity. I'm looking at rate used. But the quantity has to be in a mole quantity because the rate used is in a mole quantity or number of particles, 1 to 2. I can't say that I can't use these grams. So the very first thing you'll do is convert them to moles. Again, the most common answer here is equal quantities. This is using up faster, so it's a limiting reactant. You can't make that assessment. You don't know that we have equal quantities. So let's find our quantities. This guy here, 12 plus 4 is 16 grams per mole. This guy is 32 grams per mole. Alright, notice that's twice as heavy. So there's half as many of them for a given mass. And it's being used up twice as fast. So that alone, analogy, should tell you that this might be my limiting reactant. But let's just flip it over now. 25 grams, dot line, get rid of grams and go to moles. 1 mole is 16 grams. Go ahead and calculate. 25 grams, get rid of grams and go to moles. 1 mole is 32 grams. You should note that you should have half as many particles here. 25 divided by 16 equals 1.56 moles of, and this is the CH4, alright, and of course if you divide it by a number that's twice as big, 25 divided by 32, you should get half as big a number, equals 0.78 moles. Alright, so now I have my quantities. I have less of this guy and a higher rate used. This is my limiting reactant. Done. Without a shadow of a doubt. Okay? So now, let's plug our moles in. 1.56, 0.78. Run this guy to 0. And now we start using our stoich ratios. 2 to 1, 2 to 1, 2 to 2. Alright. Make sure you show your work even if it's small. ICE table is not a form of work that AP will accept. So that means you don't have to do it. 0.78 at a 2 to 1 ratio equals any kind of work. Okay? I know these are simple proportions. All you got to do is tell what you did in your calculator. So minus 0.39 plus 0.39, and this is plus 0.78 at a 1 to 1 ratio. 0.78 at a 1 to 1 ratio equals 0.78. If you don't want to show your work, you could simply say that the O2 equals H2O. Alright? Equals, whatever. Find some way to indicate that you're doing something. All right, subtract. So who was limiting? Well, we got this as being the O2. How much mass is left over? So again, the most common wrong answer would be 0, but this is my limiting. How many moles are left over? So let's do that right here. 1.56 moles minus the 0.39. All right. 1.56 minus the 0.39 is 1.17. 1.17 moles of CH4 is left over. Let's flip this from moles to grams. It wants the mass of excess left over. 1 mole is 16 grams. I'm getting this from right here. Okay, so we have more than 16. We expect a number bigger than 16, but not much bigger. Times 16 is 18.7. 18.7 grams of CH4 is left over. Of course, keep in mind we started with 25, so that's okay. We certainly wouldn't want a number here bigger than 25 because that's more than we started with. How many liters of carbon dioxide are produced? Okay, so I got to jump from my limiting to carbon dioxide in moles, and then I'm going to convert that to liters. Let's do that. So I got 0.78 dot line at 2 to 1 ratio is going to be my moles. Get rid of my moles and go to liters. Of course, they're going to have to give you, assuming STP, because gases change on conditions, 22.4. And let's plug that out. 0.78 divided by 2 times 22.4, and we get 8.7. 8.7 liters. All right. Multiple choice problem. 25 grams of lead nitrate mixed with 25 grams of sodium chloride. How much mass of lead chloride solids produced and the mass of excess remaining? Okay, so we're going to do this problem here. We're going to run this thing through, but it's got a little multiple choice problem kind of on this first. Which of these estimates could be the mass of lead chloride? Think about that for a moment. PbNO3, and there should be a 2 here, plus NaCl goes to PbCl2 plus NaNO3. I just did the plus 2 minus 1, plus 1 minus 1, plus 2 minus 1, and plus 1 minus 1. So this is our potential products, and this forms a solid here. Okay, so I have equal masses. This guy has a pretty hefty weight. Let's get out our moles. And again, we're trying to estimate this here. So I'm going to estimate before I get started here. Okay, this has got a really hefty molar mass. So that means my number of particles here is in my ice table is really small. Much smaller than that guy. And they're being used up, well, at potentially twice as fast. My molar mass is more than twice. So I'm going to just come out here and just say that this is going to be my limiting reactant. Okay. So that means I'm going to consume all of these guys, all right, to produce this. Okay. So my number has to be bigger than 25. Plus I'm combining with some of this guy. So I was trying to give you an idea that 15 cannot be possible. Also, 50 cannot be possible. Some of it's going to get unused. Right? That's out. So we're down to these two. 52 definitely can't be there. Okay? Because I'm going to use all 25 of this, and I'm not going to use all 25 of this. So my number here has to be something like more than 25, less than 50. Therefore, it has to be this answer. Okay. All right, so how do we solve this problem? Okay, it's pretty straightforward. We're going to convert these guys to moles, and then we're going to just run it through. So let's do that here. first thing we need is our molecular weights. This guy is added up is 58 grams per mole. The lead nitrate, let's add that one up over here. PbNO3, parentheses 2. This guy is in the lead is 207, I believe. Alright, 207. This is 14 times 16 times 3. That's 48. So, plus your 14 is 62. So this guy here is 62, but there's times 2 of them is 124. I pencil this out. 207, just so I don't screw something up. Plus 207, take my time. 331. That's big. That's big. 331. Alright, on the side, remember, your ice table is just for you, it's not work. So let's do this here. I got 25 grams of each. 25 grams. Get rid of grams and go to moles. 1 mole is 331 equals 25 grams. Get rid of grams and go to moles. 1 mole is equal to 58 equals 25 divided by the 331 is 0.075, 0.075, and 25 divided by 58 is 0.43, 0.43. And let's start putting our numbers in here. 0.075 and then 0.043. Alright. Kind of similar, I mean, 0.43. Okay. 0.43. I should have considerably less of this, which I do. Alright, I'm estimating that this is my limiting, but again, you may not be 100% sure. So let's just try it. Minus 0.075. Alright, minus down to 0. Okay, 2-to-1 ratio. So 0.075 at a 2-to-1 ratio equals, now if you're doing some work here, really important, put your answer here. Alright, now this is backwards here. It's at 1-to-2 ratio. That's why it's important to label things, because we're going to get twice as many here. 0.075 times 2 is 0.15. 0.15, and this is of NaCl needed. That's important so that that work can go. That's how stingy they are. I need this work to say that's this calculation. If I don't put the answer there, I just put it down, minus 0.15, they're not going to know that this work came with that number. So really important. That is something that always catches kids. 0.43 minus my previous answer is going to be 0.06 excess. 0.064 excess. Alright. And then, alright, I've guaranteed I know how much mass of solid is is remaining. How much is produced and how much mass is remaining. So now I can convert this guy to grams, and I'll jump to here, alright, from my limiting, and it's a 1-to-1 ratio, so plus 0.075. I will put this guy to grams. Let's do that quickly. Need the molar masses. I got to use my molar mass of that guy. That's 207. Alright, 207 plus 34.5. 35.4 times 2. Alright, so 35.4 times 2 equals plus 207 equals 257. 257 grams per mole. Okay, so 0.075, get rid of grams, go to moles. 1 mole is 257 grams. So I have less than, again, we want to be estimating our values here. What do we have? Alright, so it's going to be 0.075 moles. Get rid of moles. and go to grams. It is so easy to make these mistakes. And I just caught one there. So why did I catch it? Because I'm using my pencil less in my head. In your head, it just goes away. 257 times 0.075 gives me 19.3. 19.3 grams. All right. And the last calculation we have here is just converting the excess to grams. Weighs 58 grams per mole, 0.064 moles. Get rid of moles and go to grams, 1 to 58. 58 times 0.064 equals 3.71 grams. You use 3 sig figs there, but good enough. All right. This is our last question here. And we're adding in a thing called percent yield. All right, so let's take a moment here and let's run this thing through. We're using adipic acid. Adipic acid is a material used for the production of nylon. It is made made commercially by the controlled reaction of cyclohexane. The reaction is below here. So we have this. Well, I should say that this is looking at the production of nylon. This has got oxygen in here. I'm not sure. Okay, we'll go with it. Looks like an unusual reaction here, but whatever. Assume you're carrying out a reaction of 25 grams of cyclohexane and excess oxygen. What's your theoretical yield? Okay, so this is what's on paper. That's really important. That's on paper. So let's run this thing through. 25 grams of this. How much of this am I going to get? Alright, so let's go from, I'm just going to go out, because I'm access this, I'm just going to jump. This is not my limiting reactant. I don't even have how much oxygen, excess oxygen. Jump from here to here. Can only do that in moles. So 25 grams, get rid of grams and go to moles. 1 mole, add the molar mass of that guy. Then add a 2 to 2 ratio. There we go. And then I'm going to convert this back to grams. Get rid of moles and go to grams. This is my pathway, and once I have my pathway, the rest of it is just labor. Okay. All right, get the molar mass of this guy. So we got 12 times 6 equals 72 plus another 12. So 72 plus another 12 equals 84. So this guy is 84, and then this guy here, it's got a little bigger here. So we got 2 for the hydrogens, plus 6 times 2, 6 times 12, again is 72, plus 8 for that guy, plus 64 is 64, yep, plus 64. Now let's add all these together for the whole weight of this thing. Plus 8 plus 72 plus 2 equals 146. Okay, 1 to 146 grams to 1 mole. That's why those units are so nice to keep you on track. Let's run this through here. Okay, 25 divided by 84 times 2 divided by 2, I'm going to nix that calculation, times 146 equals 43.4. 43.4. That's the amount of grams that if you were absolutely perfect, that's what you get. But we're never perfect in real life. The more and more we get to spend time in lab, you realize that, man, things just don't work the way they want to. And we only got 33%. Okay? What is your percent yield of adipic acid? This is a little thing I just kind of mentioned to people. If you have 10 seeds and 8 sprout, what's your percent yield? It's 80%. So it's what you actually got, which is the 8, which what you're supposed to get, which is 10. All right? This is a theoretical. Times 100. And there we go. Let's run that through. You actually got 33.5, and that has to be given. Divided by the 43.4 times 100. All right, what we got here? 33.5 divided by 43.4 times 100 is 77.1%. I've even seen them mark it wrong if you don't have the 100 on there. That's how they are. So, gotta be showing all work. Ending presentation there. Thank you very much.